Hello, and welcome back to Paleozog PCs, the dumbest non-automotive channel on YouTube. So, we're back with part 2 of repairing a TRS-80, I guess for Tandy. So, if you remember last week, in that somewhat disjointed video, we got our new TRS-80 and showed what was wrong with it, which is the video all going all wackety, 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 wackety. So we disassembled it. We noticed that the inside of the keyboard smelled like something died in it. That has been cleaned up with isopropyl alcohol now, so it doesn't smell bad anymore. And we dug into the video circuitry, which of course is our obvious candidate for messed up video. So if you recall last week's episode, let me just grab this here paper schematic. If I'm feeling ambitious at edit time, I might put up something on the screen, but we'll see how much effort that's worth. So what we were concentrating on last time was this IC right here, Z6, which handles the horizontal sync pulse generation. Now, as we went into last time, so this circuit, all three steps here, all these little triangles, these are all 6 inverters that are inside of this circuit. It's 74 CO4. Coming in on pin 13 is the horizontal drive signal, which was basically, I showed you that picture of the counter chain. It's the signal from that essentially says, okay, we're done displaying characters. We're in the horizontal blinking area. Sometime in here should happen a horizontal sync pulse. So this inverter actually does 3 different things, and even though it's a digital circuit, it actually behaves in an analog manner during parts of this, sort of. So the first step here is that drive pulse, which is coming from TTL circuitry, and this is CMOS. Now the difference between those two is they're both digital circuitry. They have an on and an off, but the difference is at the time, classic TTL and LS circuitry was quite a lot faster than CMOS circuitry. So it was used for most of the TRS-80, but it's kind of sloppy in that it doesn't run very close to the rails. So you think of a perfect 0 would be 0 volts, and a perfect 1 would be whatever the supply voltage is, 5 volts. TTL tends not to run that close to the rails. Like a 0 can be about 0.8 volts, and a 1 is expected like it's got to be better than 2.7 volts. That's off the top of my head. So the CMOS tends to run much closer to the rails, and it uses less power. It's a better, except back in the 70s it was quite a lot slower than TTL. So the TRS-80 specifically used CMOS in this section because they wanted to clean up this pulse, make it sharper, and have a bigger swing between 0 and 1. So the first thing that happens is that drive signal comes into here on pin 13, and it's inverted twice. And all this does is it cleans it up from a TTL level signal to a nice sharp digital CMOS level signal. Now the next step is interesting, and this is why they wanted to get it running closer to the rails. So the first stage, which is achieved by a capacitor and this resistor, is this system depends on the analog aspects of charging a capacitor up to a certain voltage. So it's used here. So the drive signal, when it comes in here, can be delayed by some amount by depending on, by how much voltage you let through this resistor, it slows down or speeds up how fast this capacitor charges. And as that capacitor charges, it does less voltage drop. So it'll eventually reach the threshold in which these will fire. They will go from 0 to 1. And you see that gets inverted twice. And that goes to the next step over here. So this is the delay section. I know I sort of mentioned this the last time, but I just want to be clearer about what it does, because that's going to make some sense in a minute. Now, the next step, the last step here, is essentially, it's like the transition that it's getting from the H-drive pulse. This section right here, so the H-drive is actually high for almost like 2/3 of a line, and that's way too wide to be an actual H-sync pulse. So this section, which consists of another capacitor and a resistor to ground, that determines how wide of a sync pulse is created by the transition that's delayed here. So that's what the last two gates are for. So we were effing around and thinking this circuit could be dead. And I also poked at like some of these resistor values and ended up kind of wasting my time. And anyway. So this is the lesson that if you have a big tool, use it straight out. Because I said in the last video, we're going to pull out the oscilloscope and see what's actually happening here. Because I was starting to suspect something else. So let's take a look at what the oscilloscope says is happening here. So right now, you see this, I've got a black and a white probe right here. And where I've stuck these probes, I've jumped ahead a little bit. I initially had one of the probes on pin 13 here, looking at the TTL signal. But to get a better, cleaner look, once I determined this part was working, so I actually stepped all the way through and I put a probe here, put a probe here, so where it is right now is the white probe is actually here after we've accepted the H-drive signal and cleaned it up to a nice sharp CMOS edge. And the black pulse, the black clip, is actually over here all the way at pin 8, which is all the way at the end of this. So we're essentially seeing a cleaned up version of what goes into the circuit over here. And we're going to delay and the pulse stretch. So we're seeing what is actually fed out into this circuit, which is what mixes it with the vertical pulse and creates the composite pulse sync signal that ends up going up here. So let me go ahead and reposition the camera and show you what the oscilloscope sees there. Okay, so here we are seeing the scope on the screen. Now the lower trace here is the H-drive signal. And like I said, you can see if you fiddle it around, it is almost as wide as the part of the, there's almost as much of it as there is not H-drive. So the counter chain, it's like halfway through a line counter chain. And the whole thing from here to here, this would be a line of characters. So text would be filling this up. That's so a vertical, a horizontal line with NTSC is about, it's like 15,000 hertz. So it's about it's about 63 microseconds, I think. If I get that wrong, I'll put a caption up. So if we look at this little squares, we've got this squared out. I scaled it so we're about 1, 2, 3, 4, 5, 6 squares long. So each square here is about 10 microseconds or about 100 kilohertz. So anyway, you can see how we just got nothing but garbage on the screen. One thing I noticed straight away when I started playing with this is I mentioned there's this variable resistor right here, and that's essentially a horizontal positioning resistor that chooses where a line starts on the screen. So this is, as you see, this is about where you'd want it on the screen. I mean, if I fill up a whole line with letters. Oh, this is exciting television right here, hitting the B key over and over and over and over and over and over. Anyway, you can see we're pretty well spaced right here in terms of where horizontal position. But anyway, I started playing with this, and again, this increases, basically this increases or decreases the amount of charge that needs to go into that capacitor before it triggers the next step. And I noticed that it gets swimmier and swimmier the farther this way I go. And if you look at the trace, it may not show up very well on the camera. This actually gets messier and messier. You can see that this is getting a little wider, but it's not actually making the pulse wider. It's just actually, if you look really carefully, it's wiggling around where it starts and ends. So it's covering a larger and larger range of positions. Conversely, if I crank it back the other way, where there's less and less charge required, you can see it actually gets clear. And in fact, it's almost completely clear when the pulse happens with almost no delay at all. Now that is very interesting, because that implies, well, first off, this is all working correctly. You know, greater, it's behaving how it's supposed to. The pulse is moving as you would expect based on the charge of these capacitors. So all the analog components of this seem to be working, except for the fact that the longer the capacitor needs to charge, the messier it gets. This also pretty much absolves the digital portion of this, because there's nothing, it's either on or off. If it was like frantically dinging around, we would probably see it in this phase, and it's not. It's rock solid here. Now, so again, if I crank this back to where it's supposed to be, it's going to get messier and messier. Now, the other thing you may have noticed that's weird is the low level is a line. The upper level is all wide. Why is it all wide like that? In fact, if you look at it carefully, you almost see like a rapidly changing sine wave in it. So, this is an old-fashioned scope. There's nothing digital about it, but you know, scopes still have some intelligence, even these old analog ones. And they use something, there's a feature of them which is called triggering. And triggering is when the sweep across the display here, you can tell the scope to derive that from some action, something it detects, like when this value goes up or goes down or whatever. So, or you can use actually an external trigger, like if you want to see how something is going compared to some external reference, some clock or something, you can use actually another probe and do that. But this is using internal triggering right now. So right now we are triggering based on when the horizontal drive system sweep changes. So if we scooch this over here, you can see we're using internal triggering on channel 1, and we are triggering on the drop from a high to a low right here. So why am I explaining this? Well, first off, this explains why, like when you saw I moved the knob back and forth, we saw this go back and forth, but this stayed stable. Like, just for fun, if we like switch the trigger, so we're triggering off the other one. Now, first off, you notice it gets messier, because I mentioned this is messier. Now, if we crank this around again, we'll see the bottom one moves around, because we're now triggering on the falling pulse of this. But it's shakier because this is shakier, unless it's cranked all the way over, in which case it's looking pretty good. So when I saw this, and I admit I cheated a little bit, read ahead in the book after the last video, so I get an idea where we're going this time. This hash going on up here, I started thinking, and I was getting some subtle hints that maybe do we actually have a power problem going on? It's not anything. This circuit is fine. Everything I've done with a circuit makes me think it's fine. Is what's powering the circuit a problem? So let me do something really quick. I'm going to move the probe that's on the top here from the pulse output. We're removing it from pin 8. And I'm just going to stick it on the power supply for this pin, for this thing, which I believe is going to be pin 14 up here. Look at that. So let's go back to the other trigger. So now you see we just have a high level up here. We're basically getting 5 volts constantly because I stuck it on 5 volts. We're triggering on the bottom again. When I flip the trigger, if this was just on a line, if this was just stable voltage, there should be nothing to see when I flip the trigger because there's nothing to trigger on. Instead, look at that. I have a little sine wave. Now remember I mentioned how we derived that each one of these squares is about 10 microseconds. So anyway, it's like about 100 kilohertz. Look at this. We have, if we go from peak to peak, our peaks are almost on the lines. So we have an almost 100 kilohertz wave in our power supply. See, and this doesn't change when I scooch this around. It's constant. So that's bad. This is 100, and if we look at this is set up so each square is vertically is about 2 volts. We have over a volt peak to peak sine wave at the top of our voltage regulation. This explains so much. So this explains, I mean, not only, in addition to you see we've got all this waviness on the screen. This explains why not only do we have the unstable horizontal sync, because remember I talked about we have these capacitors here which have to charge in order to do the delay of the pulse and also the pulse width itself. But I think this one is the one that's really causing the visible symptoms. The frequency of this is almost perfect to cause this capacitor to charge at rates varyingly enough that we're going to end up with longer and shorter delays basically every scan line. And and again, it's because this is like a fraction of the line length, that explains why it seems to be why it can look like it's a rocking pattern. Now, also, this is going to screw up, subtly at least, every delay line in the machine. It's going to screw up all the amplifiers, like the output output transistors for this. Everything is going to be screwed up by this. So, I think we've found our culprit. So, what do we do about that? Let's go back and look at the board. Last time I did a little story time with this power supply thing, reading it out loud, and I'll be honest, I didn't really quite understand it. So I still don't completely understand it, but I understand it a little better. So did the homework. This right here, inside the Radio Shack manual, is a diagram of a circuit called a 723 regulator. A 723 regulator was a voltage regulator that was invented by an analog genius in the late 1960s, and it was extremely common for about a decade before it was largely phased out in use in like computer use by simpler fully integrated regulators like the 7805 series and such. Like if you open up a Commodore PET and you look in the voltage regulator section, and again, if you like an S100 machine, even like machines older than this, in an S100 machine, like every card has its own power regulators on it. It's usually like a 7805 and a 7812, which is just one can. This uses these two little black ICs right here, which are DIP format 7812s. And the story supposedly behind that is that Radio Shack chose to do that because even though it's not just a one can solution, instead of it, a 78 would just be like one thing, like here. This was actually cheaper to use one of these, and then this can drive a little bit of a power load by itself, but usually in a circuit like this, it's connected to a more powerful external op amp, which in this case for the 5 volt is this big chunky guy right here. Runs nice and hot. This is used to control the external op amp, which is the thing that actually drives the current. So this uses a Zener, what's called a Zener diode, which is a diode that passes current, passes voltage once it reaches a certain point. It's basically acts like a resistor until it hits a magic point, and then it starts outputting power. So this uses, built into the circuit, if you were doing this by hand, you'd have an external Zener diode. This has built into it a Zener diode, supposedly very, very precise over a wide range of temperatures, and it outputs a voltage reference. Now, actually, I'm not going to go too deep into this because analog circuitry is not my bag, and I don't want to make too many mistakes. But I will link in the description of this some links to people smarter than me that know their stuff here. But basically, it outputs this voltage reference, and then it uses a feedback loop with this component right here, a feedback amplifier, that based on the reference and some voltage dividers with external resistors, including a variable one on this where you can set the power, it regulates when the external op amp is on or off, and thereby produces regulated power at the voltage you want. So the important part of this is essentially a flaw, well, not exactly a flaw exactly, but a factor of these circuits is, again, there's this feedback aspect of it. So basically, when it's driving the external power drive via one of these outputs, there can be some delay between, oh, I think you're not driving, there's comparative, I think it's too low, think it's too high. It's making those decisions analogly, but there's room for it if there's a lag in the system where it can start oscillating. So it can end up switching itself on and off, auto oscillating at a very high speed. So the chip on pin 13 has this compensation pin, which you're supposed to hang like a capacitor off of to help damp out these oscillations and make it stable. So after reading those other docs, I was able to understand the part right here, which says C12 is connected performs the same compensation function as a C13. So this is what leads me to believe we have a problem with this voltage regulator or one of its surrounding components. And so let's poke. So the first thing I think we want to do, I'm going to bring out my voltmeter here. It's pin 4. No, sorry, pin 6. Pin 6 of this device is the reference voltage. So first thing we're going to do is let's probe pin 6 on this and see if it's producing the correct reference voltage. It's supposed to be a little over 7 volts. And 7.9 volts looks pretty good. And its spec is 715, but I don't know how much I trust this thing, this meter, so it's fine. Now, there should be on pin 5, should be the voltage, you know, that we've set with the divider resistors. That should be the voltage we're aiming to regulate at, drive the pin at. So on pin 5, we should see 5 volts, which we do. So that's looking good from the voltmeter's point of view. But let's go back over here and look at the scope. I am going to pull off the probe that is on the bottom there, because I want to see if those are oscillating like this is. So if I look at pin 6, it is not, or at least not. I think the amount of oscillation in that there could just be passing through the ground. It's basically smooth. So if I look at pin 5, it's also smooth. So the oscillation does not seem to be happening on the reference side of the voltage regulator. So there are several suspects. So if we look at the schematic here, check that, it's okay. Now there's the compensation capacitor right here. That could be bad. And that is what I suspect. Now it's also possible there could be some problems with this reference resistor. Now it could also be there are 2 capacitors on the output which are meant to damp things out. There's a tiny little like a 100 microfarad, and then there's a larger, sorry, yeah, the 100 microfarad, yes, picofarad, and then a 10 microfarad. So this is a electrolytic can, and this is a tiny disc. And the reason there's this is for bulk slow transients, like if there's any 60 hertz wave going through. And the smaller one is meant to damp down higher speed transients. I doubt it's actually the electrolytic can, because the frequency of this would be too high for an electrolytic can like that to help much. It could be C14, but my money is on C13, or at least I think it's the place to start. So what I'm going to do is I'm going to turn this off, and I'm going to grab a random small capacitor. Now the capacitor that's in there this guy is it's 470 picofarads. I actually don't happen to have a 470 picofarad. I have 100s, 220s, 330s, 680s. So I'm going to take a 220, just about half the size, and I'm going to hold it in there against the legs of this while we power it back up. All right, I'm going to stick this in here and hold it against this. Try to get a nice tight feel on it. Holding it in there and powering it up. And look at that! Look at that! Sharp! Oh, let me turn this off for a second because we lost our the other probe fell off. Let me reconnect that because well, actually, here, let me change this real fast so we have something more interesting to look at. I'm going to put this reference back on the horizontal drive signal so we can see how clean that looks now. Hopefully it'll have a nice sharp point on it. Okay, we're clean. And look at that. We have a completely clean transition there. We win. I'm a very happy pterodactyl. Okay, so I guess the question is, should I just go ahead and desolder that? Or I'm thinking, let me try, so that is like pin sharp. Let me try a different value. Let's go a little bigger. We don't want to put too much capacitance on it. We also don't want too little. Now, when it's not driving external op amp, the old original design docs, so this is a 331 I'm going to stick in here. Original design docs say that when you're not driving external one, you probably can get by with a 100 picofarad. When you are driving external amp, you probably want somewhere around 500. But that looks really good. That is rock solid. So I can't really see any difference. Now, admittedly, I am running through a digital conversion. Maybe I should try it on a tube. But we fixed our TRS-80. So let me just show you what I'm doing over here. So yeah, holding the capacitor in. Oh, you see, it popped out, and there we go. we're back to that nice, that shitty wide top there. So let's turn this off. And what I'm gonna do is I'm gonna grab a soldering iron. I'm gonna tin the ends of a capacitor, and I'm just gonna hang one in there without even bothering to solder and desolder the old one. I'll just solder it to the legs of the old one, and we'll see what that gets us. After I do that, we should recheck the voltages, make sure it's still correct. So be right back. All right, I've got the soldering iron warmed up. So my plan is here, I'm just going to Put a little bit of solder on my tip and just kind of tin the ends, little legs of this little capacitor. Oh, Jesus, that gets hot. After I'm holding the capacitor in something other than my precious little fingers. Alright, so we're trying that again. Holding the capacitor in the pliers. And just get it nice and tinned. Then we're going to put a little more tin on here, and I'm going to try hooking it up to the capacitor that's in here. All right. So let's plug the power supply back in. Hope we didn't kill anything. Voila! So yeah, let's take another look at our scope. We're triggering on the horizontal drive signal again. Let's switch back to trigger from that. There's like nothing. So I had the milliseconds per division set to 10 before, so I'm gonna crank it to, that's faster. Let's go slower. See if there's any more ripple. And that looks really, really clean. So if we flip this back to the other trigger, you can see. Yeah. So there you go. That was the problem with our eBay bargain TRS-80. Simple issue with the voltage regulator. And yeah, there we go. We have a working TRS-80, or at least this much works. Remains to be seen what else is broken. But yeah, so I guess we should talk about what we learned here. So I think the big lesson from the last two videos is if you have an oscilloscope, pull that sucker out first thing. Don't. I kind of farted around in the first video trying to just shotgun stuff and poke around with the voltmeter. I was thinking that might be more educational because I know scopes are expensive. But I think this shows even a beat up old Tektronix like this, which, you know, if you eBay one of these for less than $100, it's not going to be perfectly tuned anymore. It's going to be sort of, this one's got some inaccuracies. But even an old scope like this that doesn't magically measure values or count things for you is invaluable, because as you can see, as soon as I put this onto the signals, I could see that there was something weird going on with the voltages. So even though it wasn't what I was looking for, it immediately clued me in. So let me go ahead and undo the scope here. All right, moment of truth. We've got this guy wired up. The Apple monitor's warmed up. Let's go. And there we go. It looks pretty good. It's a little bit. Now let's get a line of characters. Now, one thing you have to be careful of, actually, when you're using these old Apple monitors, is Apple actually had slightly non-standard horizontal positioning with their monitors. So if you adjust it so it's centered on an Apple monitor, it might actually be a little bit off on another monitor. So I'm going to call that good enough. Okay, a couple more editorial notes before I throw this back together. So you might remember we took the case apart last time. This post was broken off. I have glued that. I had some all-purpose plastic pipe cement, so hopefully that will hold together. Now the other thing we ran into is the machine uses these little spacers. Got a few in the bag here that are made out of some weird material. I don't even know what. And some of them, you see, have hardened up almost like a resin, while there were others that are squishy, rubbery, gross, and sticky. So for reassembly, I went ahead and I happen to have some aquarium siphon tubing that is almost exactly the same diameter as these things. So I went ahead and cut some donuts out of that. So that's what I'm going to try to use to put it back together. Also, for future reference, I've taken pictures of the other side of the board while these switches wire up, so I can reverse engineer that later. One thing that is kind of interesting about this machine is it doesn't have, you see, it's got the satellite board for layer 2 basic, level 2 basic, but it doesn't have Radio Shack. There was an issue with loading from cassette tapes with these, and Radio Shack issued a free fix called the XRX, which worked around the problem. This does not have the XRX satellite board on it, so that's interesting. I don't know if they didn't take it into Radio Shack because they voided their warranty with all this stuff, or what. So interesting. Anyway, let's see if we can get it put back together. Got some towels to protect the keyboard. Now, one thing that's interesting about these early model ones, the later ones came with an Alps keyboard that was all one piece. These early ones, this is actually just a little satellite piece, because they originally came with just the alphanumeric part, not the pad. So this is actually pretty Mickey Mouse the way this fits together. So let's see how much fun it is to get it back together. Alright, after all that screwing around, I want to make sure this thing still works. That was horrible. Cross our fingers. And that there is one repaired TRS-80 Model 1. Whew. Man, my hot take is these things suck to take apart, and especially to put back together when they have a ton of wires hanging off them. So, I think this is probably a good place to end today. Thank you for watching. I have many plans now that I have a working TRS-80 here. And hopefully next time will not be in 6 months again. We'll see how it goes. So, again, thank you. Have a happy Septandy. Good night.